All right, so that's a non-uniform field. Now I'm going to fire a particle positive charge into a uniform field. So first I'm going to draw a uniform magnetic field. I'm going to fire stuff into it. So let's see, uniform field. And I'll let it come out of the board. I'll get that fairly uniform. Okay, so now I'm going to fire a positive particle into the field. Use a positive charge, and we're just going to shoot it at the field. There's this velocity. Well, I erased my magnetic force. Force is still QV cross B. Now I'm going to figure out the direction of the force right here. So QV, and the field points out, cross B. So at that point, the force points that way. And you can see what the force is going to do. It's going to cause that particle to turn. And it's going to turn like this. And at each point along this, the magnetic force is going to be the same strength, but towards the center. So we got a situation like if you're trying to, have a mass at the end of a rope, and you're rotating around your head. You're constantly pulling the object towards the center, and it goes in a circle. All right, so let's work this out. So first, the kinetic energy is constant. The magnetic field does zero work. All right, so the kinetic energy is 1/2 mv squared, the constant. And that means the speed's constant. All right, so here the field points out, and the velocity is always in the plane of the board, so the angle between the field and the velocity is always 90 degrees. We're also going to have a constant magnetic force. So the magnitude of the magnetic force is the magnitude of QV cross B. Like I just said, it's V and B are always at right angles. So the magnitude of this would be QVB sine 90. Sine 90 is 1. So this is just the charge times the velocity times magnetic field. Okay. So we have a constant force. This means the particle travels in a circular orbit. And we're not going to figure out how big an orbit that is. The acceleration of anything moving in a circle is called the centripetal acceleration. AC for that is just V squared over R. So we've got the force, we've got the acceleration, so if we apply Newton's law, Newton's second law, magnetic force, which is QVB, equals the mass times acceleration, AC, that's mv squared over R. So for a particle moving in a circular orbit in a magnetic field, QVB is mv squared over r, and yes, you can cancel one of the b's out. So let's do an example of that. Let's shoot a proton into a big magnetic field. Now you can get magnetic fields of this strength on campus, but you're not going to get one at Walmart. So from Walmart you can buy a field of about a Tesla in a nice, one of those nice chrome plated magnets. Your doctor's office, you probably get a field of 2 to 4 Tesla, and on a university, up to 20 Tesla probably. So a proton shot into a 10 Tesla field, orbits with radius r equals 10 centimeters. How fast is it going? All right, so our starting point is magnetic force is QVB equals mass times centripetal acceleration. That's mv squared over r. And what we're looking for is the speed, so we're going to solve this for v. Okay, we're going to cancel one v there, multiply by r, and divide by m, so QV r over m. All protons are 1.6 times 10 to the minus 19 coulombs. We're given the field is 10 Tesla. The orbit is 10 centimeters or 0.1 meters. The mass of proton is always 1.67 times 10 to the minus 27 kilograms. Now, you don't have to use formula card space. If you need the mass of the electron, the mass of the proton, I will give it to you. If you plug this in, that's 9.6 times 10 to the 7th meters per second, or about 1/3 c, the speed of light. So in this case, this is a point where we're right on the edge. We should be worrying about relativistic effects, but in this class, we're not going to worry about them. So there would be some corrections for this system because its speed is sufficiently close to c, but at 1/3 c, perhaps 10% correction. Okay, now you know that all magnetic fields are dipole fields or high order fields because of no magnetic monopoles, and now we want to introduce magnetic dipoles. So I think I'll clean the board up there.